Dear students, today we are going to discuss about a special spectroscopic technique called rotational spectroscopy. I think you already heard my talk on the introduction of spectroscopy. So there we discussed that rotational spectroscopy is come in the region of microwave. For explaining rotational spectroscopy, first we need a model called rigid. A rigid rotor can be drawn by this one mass connected to another mass by a rigid line. This is not elastic. Okay. So this particular model is called rigid rotor. So for the rigid rotor, it needs a rotational axis, and this particular rotation is quantized. So that is the basic principle behind rotational energy. One of the fundamental concepts here is the rotational spectroscopy is shown by the molecules which has a permanent dipole moment. So for example, the molecule like HCl, you know that in H there is a partial positive charge and there is a partial negative charge on chlorine. So this can be act as a dipole. So we will first check how a dipole causes the signals. Okay, that is the origin of rotational spectroscopy. So now we can consider a dipole like this. I am writing the plus here and minus here. So this is a dipole, and now the dipole is rotating. Okay, suppose the dipole is rotating like this. That means now the negative charge is here and positive here, and again it is rotating like this. Means what happened? This negative will be here and positive will become here. That is why this dipole is rotating. Okay, so we can represent like this rotation as the dipole moment symbol. You can see like this. Okay, and like this you can represent. Okay, that is why it is rotating. Okay, like this it will come, and like this it will come. Okay, and if I draw the graph of the signals caused by this, it will be like this. Okay, so starting from here, we will go like this, and finally, so it will produce the electrical signals. That means the rotation of the dipoles will make some electrical signals. So this electrical signals, actually the rotation is caused by the microwave. Okay, so the electric field of the microwave will make the dipole rotating. Okay, so that will cause the production of signals like this. This is the origin of rotational spectroscopy. Same type of phenomena is happening in the working of microwave oven. You know that in microwave oven we are not supplying heat from outside. It is called the internal heat generated by the microwave. You know that in our food, suppose you are baking a cake, in our food it consists of H2O molecules. You know that H2O molecule has a permanent dipole moment. So when microwave falls on this particular food item, H2O will rotate. So during the rotation, it will produce heat, energy in the form of heat. So due to that heat, this food will become cooked. Okay, and it's the same type of working principle you can apply for the microwave oven. The concept called moment of inertia is very important when you are talking about the rotation of objects. The moment of inertia can be explained by the Newton's law of motion. You know that already, that force is equal to mass into acceleration. Mass into acceleration. Okay. So suppose in the case of a rotating object, this force you can replace by torque. Okay. That means the torque is equal to mass. Here you can replace it by moment of inertia into angular acceleration. So that means tau is equal to moment of inertia I into omega. Okay. So this I is the moment of inertia. That means it is equal to mr square for a tiny. For the bulk moment of inertia, I is equal to the product of sum of tiny masses and their radii. Suppose when you consider a cylindrical shape like this. Suppose this is the rotational axis. This is the rotational axis like this. The mass is concentrated around the spin axis. That means it need a very less force for the twirl of this particular cylindrical shape. And another cylindrical shape I will draw here like this, and I am considering this particular rotational axis. In the case of this particular cylinder, suppose you consider a rotational axis like this, you can see that here the mass is distributed far away from the spin axis. That means it needs more force to twirl the cylinder like this. That means the moment of inertia here it is very less, and the moment of inertia here is high. Okay. Suppose we consider a bicycle wheel like this. You can see that the mass is distributed like this: m1, m2, m3, m4, m5 and m8. You can write the moment of inertia I is equal to m1 r square plus m2 r square plus m3 r square, etc. It will go like this. So that means you know that now I is equal to r square into m1 plus m2 plus m3 plus like that. Okay. So that means you can write this I is equal to capital M into r square. Okay. So here you can see three types of wheels of equal mass. Okay. So all the three wheels has equal mass. What about the moment of inertia? What about change in moment of inertia? Here you can see that in the case of this first one, all the mass is distributed through the edge of the wheel, and this particular object has high moment of inertia. And when come to this, you can see that radius is reduced, but it is equal mass, but the moment of inertia is little bit small compared to this one. And what about here? Here you can see that the mass is distributed around all the area of the wheel, but equal mass. But here the moment of inertia is very less compared to these two. Okay, so the order of moment of inertia is very high for this one, and second this one, and final. Okay, so now we can consider a linear molecule. You can have three rotational axes for a linear molecule. So one is like this, and like this. Okay, so what will be the moment of inertia here? We will just see. Okay, so here I am giving the name IB, the moment of inertia, and here IC, and here IA. First we can consider the moment of inertia IA. So suppose you are considering a molecule like this. This particular moment of inertia, this particular axis is through the bond axis. That means here the IA will become 0. But in this case you see IB and IC, you can write that similar type moment of inertia. That means IB is equal to IC. So this is about a linear molecule. Now we will see different type of molecules like this. One is called spherical top molecules, and another one is symmetric top molecules, and asymmetric top molecule. Okay, you can take an example of spherical top, that is the CH4. Okay, you know that this is a tetrahedral shape like this, molecule like this. Okay, so here you can draw the rotational axis like this. One is through this hydrogen, one is this through this hydrogen, another one is through this hydrogen like this, and okay, you can draw like this. So you can have here also this IA, IB and IC, IA, IB and IC. So in this type of a molecule, IA is equal to IB is equal to IC. That's about a spherical top. Next we can consider a symmetric top molecule. An example is CH3F. That means the here hydrogen is replaced by fluorine. So just like you can see here the tetrahedral type shape like this, but it is not perfect tetrahedral, you know. So if you draw the moment of inertia, the rotational axis like this through the hydrogen, Okay, so here you can write this IA, IB and IC like this. So here you can see that this IB is equal to IC, but it is not equal to IA. And also you can also write that this IA is not equal to 0. Okay, so next we can consider the asymmetric top molecule. So a very good example is our water molecule. You can draw the rotational axis of water molecules like this. One will be through oxygen like this, another will be like this, and another will be like this. Okay, here also you can see this IA, IB and IC, but in the case of asymmetric top molecules, you can see that this IA is not equal to IB and not equal to IC. See, when we consider the molecules with a large number of atoms, the moment of inertia calculation become very complicated. So here in this molecule you can see there are 4 type of masses. One is Ma. So this Ma is similar, Ma, and you can see this one is MB and this one is MC, and finally we have MD like this. Okay, so there is 4 types of masses, and here this MA and this MB is connected by RA, that is the radius, and here it is RD. I told you that it's very complicated when the number of atoms increases. So when you calculate the moment of inertia, it will be getting like this: I is equal to the 3 MA RA square plus 3 MD RD square. Okay, again we can consider a rigid rotor. You know that this is a model, important model. Okay, so rigid rotor I will draw like this. One mass M1 is connected with M2, and you know that there is a center of mass. So the through the center of mass I can draw the rotational axis like this, and this particular radius I am marking it as R1, and here it is R2, and whole together, that means the distance between these two masses, let it be R. Our R0 is equal to R1 plus R2, and let it be the equation number 1. Okay, this is, you know that this is center of gravity. I already told you. If this is the center of gravity, you can write that M1 R1 is equal to M2 R2. So let it be the equation number 2. Then the moment of inertia based on this rotational axis I, you can write like this. We already discussed the moment of inertia: M1 R1 square plus M2 R2 square, and you can rewrite like this: M1 R1 R2 plus M2 R1 R2. That means that is equal to R1 R2 into M1 plus M2. That is, let it be the equation number 3. From equation 1 and 2, you can write that this M1 R1 is equal to M2 R2, that is actually equal to M2. What is this R2? R2 is R0 minus R1. You can also write it for M1 and R. Now you can write your R1 is equal to M2 R0 divided by M1 plus M2, and your R2 is equal to M1 R0 divided by M1 plus M2. Okay, so if you substitute the value of R1 and R2 in equation 3, you will be getting I, that is the moment of inertia. I is equal to M1 M2 divided by M1 plus M2 into R0 square. So this is the moment of inertia equation, and here this particular value, that means for a rigid rotor, that means it is just like a diatomic molecule HCl, and here you can see M1 M2, you see here M1 M2 divided by M1 plus M2 is actually known as the reduced mass, because here two masses are there. So in there are other cases, suppose it is one mass means mr square, but here it is 2 masses are there. So, this particular value is known as the reduced mass into radius. So, this is the final equation for the moment of inertia of a rigid rotor. Okay, now we are going to the rotational spectroscopy part. For explaining rotational spectroscopy, first we need the information about the rotational energy, and the next we need the information about the energy levels. The first one rotational energy, next we need energy levels, and third one is energy level spacing. And you know that the backbone of a spectroscopic technique is called selection rules. So, the next we need selection rule, and finally after the explanation of selection rule we will reach in the spectrum. So, this is the order we are going to discuss about the rotational spectroscopy. Okay. So, let us start with the rotational energy. I already told you that here the model, our important model is called the rigid rotor model, and the rotational energy. So, it is actually coming from the quantum mechanics. The energy of a rigid rotor can be write like this: E. I am just explaining this as EJ. EJ is equal to h square by 8 pi square I into j plus 1 joule. So, it is in joules. Okay. So, you see what is this J? J is known as the rotational quantum number, that is J can be 0, 1, 2, 3 etc. You already studied in your quantum mechanics. Okay. So, this is the equation, and you know normally in spectroscopic techniques we are not taking the unit joule, we are normally converting this to centimeter inverse. So, in order to convert this particular equation to centimeter inverse, you have to divide this EJ by h into C. So, now that is equal to h, our equation will be h 8 pi square IC into j plus 1 centimeter inverse, and this part of the equation, that means the first part, okay, h by 8 pi square IC, can be represented as B, that means the rotational constant. So, now our energy equation you can write like this: EJ is equal to BJ into j plus 1 centimeter inverse. So, this is the final equation for this much centimeter inverse. This is the final equation for the rotational energy. Then we will think about the rotational energy level. You see, our equation is EJ is equal to BJ into j plus 1 centimeter inverse. I told you that this B is the rotational constant, J is the rotational quantum number, can have values of 0, 1, 2, 3, etc. So, let us give J is equal to 0, then your EJ is equal to 0. Okay, you can give values. So, suppose J is equal to 1. J is equal to 1 means 1 plus 1, 2 into 1, 2. That means Ej is equal to 2b. Okay. So, when you give j is equal to 2, our Ej is equal to 2 plus 1, 3, 3 into 2, 6, that means 6b. And finally, you can see that it is coming like this, 0, 2b, 6b, 12b, 24b, like that it will go. Okay. So, now we have the platform. Okay. Now we have the energy levels. We have rotational energy, we have the energy levels. Okay. So, now you can draw the energy levels. The first one, you see we will draw j is equal to 0, j is equal to 0, and the next one j is equal to 1, that is corresponding to the 2b. The next you see j is equal to 3, 2, that is the level is equal to 6b, and the next one is your 12b and the 24b, like that it will go. You see when the energy increases, the spacing, you can see the energy level spacing will become increases. Okay. So, now our platform is ready. Okay. So, that is the energy levels. The next one is energy level spacing. That also we explained, energy level spacing. So, in order to find out the spectra, that means the next one is spectra. I told you that we need a very important concept called selection rule. So, normally the selection rule is coming from the derivation of the Schrodinger equation of rotational energy. Here the selection rule is equal to delta j is equal to plus or minus 1. So, what is the importance of this plus 1 and minus 1? So, here plus 1 means absorption, plus 1 means the absorption, and delta j is equal to minus 1 means the emission. You know that we are dealing with the absorption spectroscopic technique. So, we will consider delta j is equal to plus 1. You see this is molecular spectroscopy, that means the molecules are jumping from one level to another level. So, the beauty of this type of subject is the restrictions. Okay. So, the restriction is given by the selection rule, that means delta j is equal to plus 1. That means for the first level 0, only first one level, that means delta j is equal to plus 1, that to this level the transition will take place, molecular transition. Another one is this level to this level, this level to this level, like this I will draw. Okay. So, here as I told you, according to the selection rule, one transition is like this, delta j is equal to plus 1, that means 0 to 1, and the next one is 1 to 2, next one 2 to 3, 3 to 4, like this. Okay. You can see the style of molecular transition like this. One more important thing is, due to this transition, there will be resulting a spectra. So, how the spectra will look like? So, for that we have to find out the gap between spectral lines or the spacing between the spectral lines. Okay. So, in order to find out the spacing between the spectral lines, we have to consider the transitions like this. That means the Ej, you know the first transition, Ej is equal to 1 minus Ej is equal to 0, That means what? You see, j is equal to 1 is 2b minus 0 is equal to 2b. The next one is Ej is equal to 2 minus Ej is equal to 1. So here you can see 6b minus 2b is equal to 4b. Okay. So what will be the next? 2b, 4b, 6b, 8b, etc. So what is the spacing in between? 2b. So that means the rotational spectral lines are equally spaced. So you will be getting the spectral lines like this. This is the first line, second line, third line, fourth line, fifth line, like this. So what is the peculiarity of these lines? These lines are equally spaced. That means 0, 2b, 4b, 6b, 8b, like this it will go. Okay. So rotational lines you will be getting. Okay. So we have started it from rotational energy, and we have find out the energy levels, energy level spacing, and we have introduced the selection rule. According to the selection rule, the transitions, molecular transitions will take place, and finally we can write the spectra. That's about the rigid rotor, explanation of the rigid rotor model.